Hello, and welcome back. We're coming up on the 2022 season for Advent of Code. Thought it would be fun to do a couple warm-up problems. This is going to be a fast one. We're doing a throwback today to 2015 and looking at day 15. For day 15, we are making cookies. We want to use exactly 100 teaspoons of some ingredients. The ingredients have different properties associated with them. So like sample input would look like this. For butterscotch and cinnamon, we have a bunch of different properties with numeric coefficients. And the idea is that if we pick some, some assignment of ingredients such that the number of teaspoons of each ingredient that we're using adds up to 100. So in this case, we're using 44 teaspoons of butterscotch and 56 teaspoons of cinnamon. These add up to 100. Then we can multiply the number of ingredients used by their properties to get some final values here. And then if we multiply together the totals for each category, ignoring calories for part one at least, this is important, then we get a final score, and it happens to be the best score possible given these ingredients. This part is also important. If any properties produce a negative total, they instead become zero. And the question is, given the ingredients in your kitchen and their properties, what is the total score of the highest scoring cookie you can make? So we're basically maximizing score by picking different different assignments for ingredients in terms of the number of teaspoons we're going to use, such that they all add up to 100 teaspoons. So fair enough. As usual, we will look at our input, 15.txt1. We can mix this together. So importantly, the problem does not mention the names of any of the ingredients. So this is just sort of extra information that we don't need. And then also, each one of the properties appears in the same order for each ingredient, so we don't need to do any sorting on the property names. So I think that we can just pull out the numeric information and put them in a flat matrix, and that should be enough to solve this problem. So what we can do is we can put together a string with all the characters that we care about. We'll include hyphen for the negative values, and then we'll use quad D for each. This is a primitive that has a string containing all of the digit characters. We'll attach that to a train where for each we'll do membership, partition, right tack. I've done this in previous problems. This is a nice way to pull out the numeric information from the input strings. That gives us this. Those are strings, so we'll want to do a for each execute here to turn them into numbers. Then we can mix it together to get our matrix. And we'll assign this to P. Now, the next thing that we need to do is we need to come up with assignments to these different ingredients. We need to pick 10 teaspoons here, 20 teaspoons here, whatever, such that the total number of ingredients that we use ends up being 100. There's probably like a mathy optimization way to do this, but I think that what we can do is we can basically just generate all of the possible combinations of ingredient assignments that add up to 100, and we'll check each one of those. Now, we probably don't want to do, just generate all possible permutations from 0 to 100, because if we take 100 to the fourth power, this is 100 million. So 100 million is a little bit large. Instead, I think that we can generate this using recursion. So we'll have a recursive function, and our left argument is going to be the number of levels deep that we want to go. In this case, we have 4 ingredients, so we'll go 4 levels deep. And then on the right, we'll have the number of ingredients that we want to use at each level. This starts out at 100. So first, our base case, we'll have if alpha equals 1, then we will return a matrix containing our right value, omega. The idea here is that anytime that you call this recursive function, we want to return a matrix. And so in our base case, this concatenate first here, this will do This basically returns a 1 by 1 matrix that contains that single scalar value. And then if it's not the base case, then we want to recurse. And so for this, basically we want to generate all of the numbers from 0 to the right argument. So if we do iota omega, let's imagine that our right argument was 100. Iota omega will generate the numbers from 1 to 100. I'm in the default IO1 here. So if we add 1, it'll generate the numbers from 1 to 101. And then if we subtract 1 from the whole array, this will be the numbers 0 to 100, which is what we want. And then for each one of these, we'll want to recurse. We want to use a train here so that we don't lose our function binding. And then on the left side, we just subtract 1 from alpha because we're going 1 level deep. And then we just use a right tack because we're using whatever the right-hand value is. Each time that we recurse, we want to catenate some value, and that's going to be w minus whatever the right-hand argument is. If you think about it, like, let's imagine that we were going to use 50 teaspoons for the first ingredient. That means that, we have 50 teaspoons left as we recurse down the stack. And then what we want to catenate is our right-hand value omega minus whatever number we're doing, so 50 teaspoons. Now, this is going to return a nested array of matrices, so we can catenate first reduce. This puts them all together, and then that will disclose the box that the final matrix is in. So if we do this, we get a nice matrix. Each row here represents a possible assignment of teaspoons, and you'll note that each row adds up to 100. So we will save this to M for matrix. For the record, we are looking at 176,000 possible combinations, which isn't too bad. Okay, now basically we want to take each ingredient assignment and then we want to multiply them by each one of our category values here from our input so that we get scores for each category. You can probably do this by, doing a bunch of rank operators or whatever. But if we look at the shape of M, which is the matrix that holds our ingredient assignments, and we look at the shape of P that holds our values for the different categories, you'll note that the number of columns in M is 4, and the number of rows in P is also 4. So what we can do here is actually we can just use inner product. This is going to be a dot product specifically. What dot product does is for each row in M, so 4 values, we are going to multiply it against each column in P. Each column represents a different category. And then we will sum the multiplied values together to give us a single score. So this is going to be M plus dot times P. And you'll see that we have 5 columns now. What we've basically done is for each row, we've pulled out the different category values for each one of our ingredient assignments. So this matrix now has our the different scores for each category based on the number of teaspoons we're assigning to each ingredient. So we can assign this to R for result, I guess. Now, importantly, in part 1, we are disregarding calories, which if we look all the way back up here, calories is the last column in our matrix here. So for our final values, we want to make sure that we're excluding calories. And we can do that by for take rank 1. So this is now a 4-column matrix. We basically cut off the calorie values. We also want to make sure that we don't have any negative values, because remember the problem text said that we want to floor this at 0, so we do 0 max. We can multiply them together to get our final value for each ingredient assignment. We can assign this to, I don't know, A, and then we're just taking the max value out of those. And it's 21, 36, et cetera, et cetera. That is indeed the correct answer. Okay, so for part two basically asks us to suddenly care about the calorie values. And we only want recipes that have 500 calories. So, and then given the set of recipes that do have exactly 500 calories, then again, we're just finding the highest possible score. So in our result matrix R, the calories are in the last column, so we can do right tack reduce R to get those values. We can do 500 equals to generate a Boolean matrix, and then we saved our multiplied values in A, so we can just use this to filter A, and then again, we are pulling the maximum value. 100, 176, 64, etc. That is indeed the correct answer. So when we put it all together, it looks like this. 4 lines, and this is a little bit wide at 43 characters, but sometimes recursive functions can get pretty long. And then if we wanted to test, how long this takes, let's say that we do a function f, we can do like this. And if we pull over this stuff, this is not going to be on P anymore. This is on omega. We can assign this to part 1, part 2, and then we can just output a string P1, P2. And if we run F on P, we get the same answers. We can pull comp X from defense, and we can see how long it takes to run F on P. And it looks like it takes 120 milliseconds. Most of that is going to be in the recursive function, I would imagine, which, by the way, the size of im, that's going to be 707 kilobytes, so not too bad. I think the result matrix is going to be a little bit bigger at, looks like maybe 1.7, 1.8 megs, something like that. So overall, not too bad. Anyway, yeah, just a short video, a little throwback. Hopefully you enjoyed it. Thank you.